Hello, curious minds. Welcome back to our channel, where we delve into the mysteries of the cosmos and uncover the secrets of the universe. In today's episode, we're tackling a mind-bending concept brought to the forefront by renowned physicist Brian Cox, the idea that the universe existed before the Big Bang. Strap in as we explore this groundbreaking theory and what it could mean for our understanding of everything. Consider the profound mystery at the heart of cosmology. What existed before the Big Bang? If before is even a valid concept, what sparked the creation of our universe? For centuries, the answer seemed straightforward: divine intervention. Renowned figures like Isaac Newton posited that God crafted the cosmos roughly 6,000 years ago. Later on, luminaries including a youthful Albert Einstein believed the universe to be timeless, eternal. Despite changes such as the birth and death of stars, colliding planets, and the rise and fall of civilizations, the universe, at grand scales and across vast epochs, appeared immutable. This perspective only shifted in the 1930s, when robust evidence emerged supporting the universe's expansion, and by the 1960s, proof of its fiery origin in the Big Bang had surfaced. Such a dramatic paradigm shift in scientific understanding hadn't been seen since the acceptance of the heliocentric model. This revelation led to two perplexing questions. What exactly preceded the Big Bang? What was the nature of space before it began to expand, and how long did it remain in that nascent state? Furthermore, as all beginnings suggest an end, what fate awaits our universe? In pursuit of these questions, English physicist Brian Cox embarked on a quest that led to groundbreaking discoveries, unveiling insights that could rival the impact of the heliocentric shift. Through his research and innovative thinking, Cox offers us a glimpse into the profound beginnings and potential ends of our cosmic story. Brian Cox has recently ignited a seismic shift in our understanding of the universe's origins. He suggests that the cosmos may have existed before what we traditionally mark as the beginning, the Big Bang. This challenges the long-held view that our universe started from a singular, extremely hot, and dense point in time. For decades, the Big Bang was not just a theory, but the cornerstone of cosmic history, postulating that time and space commenced from this intense event. However, Cox proposes a radical rethinking. Perhaps there was a pre-Big Bang era, allowing us to consider the concept of time extending further back than previously imagined. Join us as we delve into how Brian Cox's groundbreaking ideas are reshaping our understanding of cosmic events. Known for making complex scientific ideas accessible, Cox has become a pivotal figure in bringing science to the public, engaging in widespread debate and discussion. The concept of the Big Bang itself dates back to the 1920s and 1930s, when observations of distant galaxies revealed a universe in motion. This discovery aligned with Einstein's general relativity, which suggested that a static universe would be unstable. It had to either be expanding or contracting. Cox's work builds on these foundations, yet he ventures beyond, suggesting that the universe's expansion was preceded by an earlier epoch, potentially rewriting the story of the universe as we know it. The revelation that the universe is expanding dramatically reshaped our understanding of its history. This discovery revealed a simple yet profound truth. If things are spreading out now, they must have been much closer together in the past. But the expansion of the universe isn't just about distance, it also affects the light traveling through space. As time moves forward, the wavelengths of this light stretch, which means the energy decreases and the universe gradually cools. As we trace back through time, conditions become hotter and denser, leading to an era where not even neutral atoms could exist due to the extreme heat. If our understanding is correct, we would expect to find a remnant of this primordial heat today, an all-encompassing glow of radiation, cooled to just a few degrees above absolute zero. The discovery of the cosmic microwave background, CMB, in 1964 by Arno Penzias and Robert Wilson provided breathtaking confirmation of these predictions, anchoring the Big Bang Theory in observational evidence. It's natural, then, to wonder about pushing further back in time to an era even denser and hotter, where conditions were so extreme that atomic nuclei couldn't form and radiation dominated the universe's energy. This journey into the universe's fiery infancy not only underscores the dynamic nature of our cosmos, but also challenges us to ponder its ultimate origins and our place within it. Imagine a time so intense in the early universe that matter and antimatter materialized from nothing, where the energy was so great that particles and their antiparticles could spontaneously spring into existence. In this primordial world, even protons and neutrons disintegrated into a seething soup of quarks and gluons. This paints a dramatically different picture of our universe's inception, suggesting a far more chaotic prelude to the Big Bang than a mere emergence of time and space from a singular state. Now, let's delve into the truly monumental queries. What do these revelations imply about the actual genesis of the universe, if such a definitive beginning ever existed? The hot Big Bang is a confirmed event, yet it may not represent the ultimate commencement of the cosmos. It appears that rather than originating from an infinitely dense point, the early universe experienced a phase where all the energy destined to become matter and radiation was instead trapped within the very fabric of space itself. This phase, known as cosmic inflation, eventually ceased, transitioning into the hot Big Bang we recognize today. This pivotal shift didn't lead to an infinite density or singularity. The questions of what preceded inflation, or whether inflation itself had no beginning, remain tantalizingly open. One thing is clear: our journey to comprehend the universe's earliest moments is far from over, but each discovery brings us closer to understanding the profound complexities of our cosmic origins. The Big Bang might mark a significant chapter in the cosmic story, but it's not necessarily the opening scene. If the Big Bang wasn't the universe's debut, then what preceded it? The short answer is that we simply don't know. However, the long answer opens up a universe of mind-bending possibilities. Before the Big Bang, the cosmos might have been an infinite expanse of ultra-hot, dense material in a steady state, awaiting a trigger to transform it radically. This precursor universe could have been under the dominion of quantum mechanics, where the rules governing the very small played out on a cosmic scale. The Big Bang may have been the dramatic moment when classical physics started steering the universe's evolution. Stephen Hawking introduced a fascinating concept in this regard, the no-boundary proposal. According to Hawking, before the Big Bang, events were unmeasurable and thus undefined. He envisioned time and space as finite yet without any boundaries, similar to Earth being finite but edgeless. Or perhaps there's an even more radical scenario to consider. Professor Brian Cox has ventured a bold hypothesis. There was a distinct era before the Big Bang, a profound void where the universe, as we understand it, didn't exist at all. Each of these theories challenges our understanding of cosmic origins and invites us to explore the depths of what might have been before everything we know. In his captivating documentary series Universe, Brian Cox explores a profound prelude to our cosmic story, suggesting that before the Big Bang, there was an absence of matter as we know it. Instead, what existed was a fabric of space-time cradling an almost tranquil sea of energy still, yet subtly rippling. Cox invites us to envision this early universe not as a chaotic abyss, but as an immense ocean of energy permeating the void, devoid of any structure. This serene energy sea was subject to a phenomenon known as inflation, a violent stretching of space that dramatically flipped the narrative of creation as traditionally understood. Brian Cox explains this as the scientific creation story, where an unimaginable and rapid expansion, known as inflation, set the stage for everything that followed. As inflation ceased, this vast ocean of energy transformed into matter during the Big Bang, imprinting patterns of ripples across the cosmos. These variations in density within the primordial hydrogen and helium eventually led to the formation of the universe's first stars and galaxies. About 9 billion years after this monumental event, a new star, our Sun, was born in the Milky Way, accompanied by a family of 8 planets, including Earth. This sequence, from a serene ocean of energy to the vibrant life-sustaining system we call home, highlights the dynamic and interconnected nature of the universe. Nearly 13.8 billion years after the cosmic dawn, humanity emerged, stepping into the light of a universe whose origins are still a subject of intense debate and discovery. Brian Cox is among the prominent voices suggesting a radical perspective on the universe's inception, but he is not alone in this vast intellectual landscape. Recent breakthroughs in theoretical physics propose that our universe might merely be the latest phase in an eternal cycle of cosmic explosions and collapses. This notion challenges the traditional view of a singular beginning, suggesting instead a recurring bang-bound cycle stretching infinitely into the past and perhaps into the future. The tools at our disposal, a complex blend of general relativity and high-energy particle physics, provide profound insights, yet also reveal their limitations as we probe closer to the universe's first moments. The mathematics becomes increasingly intricate, straining under the weight of cosmic mysteries until it reaches a breaking point. At the heart of this breakdown is the concept of a singularity, an infinitely dense point marking the universe's proposed inception. The presence of such a singularity is not just a mathematical inconvenience. It is a beacon signaling uncharted scientific territory. It challenges the absurd notion of an infinitely compact universe and underscores a profound truth. Our current scientific frameworks are inadequate for fully unraveling the universe's earliest secrets. We stand on the brink of new physics, a frontier demanding novel theories and tools to interpret the origins of everything. String theory emerges as a powerful contender in the quest for new physics, promising to weave together the forces of gravity and other fundamental interactions under conditions of extreme energy. This model doesn't just tinker at the edges, it proposes to fundamentally explain the universe's earliest moments. One intriguing aspect of string theory is the concept of the ekpyrotic universe, derived from the Greek word for conflagration or intense fire. This model reimagines the Big Bang not as the universe's opening act, but as a spark triggered by pre-existing cosmic events. According to this view, the Big Bang was just one phase in a broader, more dynamic process. Building on the ekpyrotic premise, string theory has inspired a renewed interest in cyclic cosmology, a perspective as ancient as myth, suggesting an eternal universe that perpetually oscillates between explosive beginnings and catastrophic endings. While this idea has floated through philosophical and scientific thought for millennia, string theory provides a robust mathematical foundation to it. The cyclic universe model envisions an endless loop of big bangs followed by big crunches, stretching infinitely into both the past and the future. Although this concept is captivating, aligning it with observational data has posed significant challenges. Initial models struggled to fit the complex tapestry of cosmic evidence, highlighting the ongoing tension between elegant theories and the messy realities of empirical science. Navigating the complex landscape of cosmology is a substantial challenge, particularly when theory and empirical evidence must align. The main obstacle for the cyclic universe theory has been its compatibility with observations of the cosmic microwave background, CMB, the faint glow of radiation from the universe's infancy at 380,000 years old. Although we cannot peer directly past this radiant barrier, any theoretical adjustments to the physics of the early universe inevitably alter the observed patterns of this afterglow. For a time, the neat concept of a cyclic universe seemed more like a beautiful fiction than scientific fact. However, the torch for the ekpyrotic theory has remained lit. In recent years, a resurgence of interest has allowed physicists to smooth out previous mathematical wrinkles, unveiling new possibilities that had been overlooked. This has led to a refined exploration of the Big Bounce theory, which posits that our universe might be expanding and contracting in a colossal cosmic pendulum swing. Advocates of this model argue about the frequency of these cosmic cycles, Some suggest it's a singular occurrence, while others propose a perpetual bouncing that defines our universe. While the Big Bounce theory still requires bridging significant theoretical gaps, often requiring a bit of scientific hand-waving, its proponents contend that these gaps are smaller than those associated with traditional Big Bang models, which rely on the concept of inflation. Inflation theory, essential for explaining the rapid expansion following the Big Bang, faces its own critics who argue that it may be too convenient or simplistic to account for the complexities of the cosmos. This ongoing debate underscores the grand and imaginative scope of cosmology, where profound ideas about the universe continually push the boundaries of human understanding. Inflation theory, while ingenious, can seem somewhat contrived. It suggests an infinite number of universes, with our observable universe being just one isolated bubble among countless others. This concept challenges the idea of a singular beginning and raises intriguing questions about what might exist beyond our own cosmic bubble. On the other hand, proponents of the Big Bounce theory offer a different perspective. They propose a cyclical universe, potentially providing a more holistic explanation without invoking a multiverse. According to this theory, another universe existed before the Big Bang, with entropy increasing towards the past. This implies that time in this anti-universe could run opposite to our own. This anti-universe concept could explain dark matter as a type of ghostly particle known as a neutrino, unique to its own universe. Moreover, extending CPT symmetry, which involves the conservation of charge, parity, and time reversal, to the entire cosmos suggests the existence of a mirror image universe. In this twin universe, every aspect of our universe would have reversed parity and time. Such a mirror cosmos, operating under the same fundamental symmetries as our own, could account for phenomena like dark matter and the expansion of the universe without requiring inflationary periods. These radical ideas challenge traditional cosmological views, highlighting that there is still much to explore and understand about the nature of our universe. The concept of a CPT mirror universe suggests an intriguing possibility that it exists beyond our Big Bang, potentially predating the observable cosmos. Researchers have proposed several observable consequences for this theory. For example, neutrinos should exhibit Majorana behavior, meaning they are their own antiparticles, and one type of neutrino should be massless, a significant and testable prediction. In this model, inflation never occurred because the universe naturally filled with particles. The absence of primordial gravitational waves, if confirmed by experiments, could lend support to this theory. Understanding the universe's origin stretches the boundaries of our knowledge. We cannot determine the universe's initial state with absolute certainty, preventing us from formulating a complete theory of everything. While scientific progress has unveiled a detailed cosmic history, significant gaps remain, such as the nature of dark matter and dark energy. The question of the first cause remains open, reminding us to approach the unknown with humility. Unlike supernatural explanations, scientific inquiry relies on evidence and data rather than faith. This approach continues to drive our quest to understand the universe, even as it constantly evolves with new discoveries and theories. The Big Bang theory is the leading explanation about how the universe began. At its simplest, it talks about the universe as we know it starting with a small singularity, then inflating over the next 13.8 billion years to the cosmos that we know today. But what if there was something before that moment of inflation? Brian Cox has brought some fascinating ideas to the table that challenge the traditional timeline of our universe. Brian Cox suggests that the Big Bang might not have been the beginning of everything. According to him, it's plausible that the Big Bang was just a phase in an eternal universe, that before the Big Bang, the universe was already there in a different form. This theory aligns with the concept of a cyclic universe, or the Big Bounce theory, which posits that the cosmos goes through an infinite cycle of expansion and contraction. If the universe did exist before the Big Bang, this revelation could revolutionize our understanding of physics and cosmology. It challenges the conventional view of time and the origin of the universe, implying that the universe may operate under cycles of births and deaths, which could potentially solve some mysteries about dark matter and energy.
Welcome to Blasovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blasovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe. Live Q&A sessions with experts. Your membership will grant you the chance to participate in live Q&A sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blasovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comments.